Could we live on a world beyond Earth? Among all the planets in our solar system, Mars has always been the one mentioned most often. If a person were to stand on its surface without protection, they would be unable to breathe. And liquid water could barely exist for long. Yet what makes Mars so fascinating is that it is not entirely foreign to Earth. NASA's robotic explorers have discovered evidence of frozen water at the planet's poles, suggesting that the red planet may once have had a far wetter environment in the distant past, very different from what we see today. So what makes scientists believe that something which once seemed impossible might one day become reality? Plans are already being drawn to send humans to this distant world within the coming decades, and our journey toward Mars begins now. The journey from Earth to Mars is far from short. It typically lasts between 6 and 9 months. During that time, the crew lives in microgravity, an environment where the human body gradually begins to change. Muscles weaken, bones lose density, and the body's balance system nearly disappears. Because of this, when the spacecraft finally lands on the surface of Mars, the first challenge is not building a base. It is simply standing on solid ground. The first human steps on Mars may be slow and awkward. Astronauts may need hours, even days, for their nervous system and muscles to readjust to the sensation of weight. Imagine the moment the hatch opens. The Martian sky is not blue like Earth's, but a pale pink-orange, created as sunlight scatters through the planet's thin atmosphere, filled with fine iron-rich dust. It is this iron oxide in the soil that gives Mars its famous name, the Red Planet. Beneath their boots lies a layer of dry, powdery regolith, ground down by billions of years of meteorite impacts. But on Mars, time becomes a matter of survival. Immediately after landing, the most critical mission begins: deploying life support systems. Without a spacesuit, a person would lose consciousness within seconds. So the first hours on Mars become a race against time. Astronauts must quickly deploy pressurized habitat modules, connect solar power systems, activate oxygen production equipment, and verify communication links with Earth. As the systems gradually stabilize, another feeling begins to emerge. A deep awareness of where they are standing. Was Mars ever like Earth? Evidence from robotic explorers suggests that billions of years ago this world may have hosted rivers, lakes, and perhaps even oceans. The scars of ancient water flows are still etched across the planet's surface. Yet Mars was never built for human life. To survive here, humanity will have to learn how to live in a world that is almost completely alien. Just how hostile is Mars, really? Mars is, in reality, a cold and nearly lifeless desert. The planet's average temperature is around -63 degrees Celsius. In practice, however, temperatures on Mars vary dramatically depending on time and location. During the day near the equator, temperatures can rise to about 20 degrees Celsius. Warm enough for ice to briefly melt. But once night falls, temperatures can plunge to -100 degrees Celsius or even lower. In the polar regions, winter temperatures can drop to nearly -125 degrees Celsius. The Martian atmosphere is astonishingly thin. If a person were standing on the surface of Mars without protective equipment, the surrounding air would resemble conditions close to a vacuum. The composition of the atmosphere is also completely hostile to human life. About 95% of Mars's atmosphere is carbon dioxide. Roughly 2.7% is nitrogen, 1.6% is argon, and only about 0.13% is oxygen. It is an atmosphere that simply cannot be breathed. In such an environment, liquid water can hardly exist for long. Despite the thin atmosphere, Martian winds can still reach speeds of 60 to 100 kilometers per hour during regional storms. As these winds sweep across the barren surface, they lift billions of fine dust particles rich in iron oxide, the same dust that gives the planet its reddish color. What makes Martian dust particularly remarkable is how extremely small and light it is. Many particles measure only a few micrometers across, nearly as fine as talcum powder. Research from robotic missions has revealed that Martian soil and dust contain perchlorates, chemical compounds with strong oxidizing properties. In addition, the extremely fine dust particles can easily infiltrate mechanical joints, wearing down equipment and causing malfunctions. If humans were to inhale this dust over long periods, it could damage the respiratory system in ways similar to lung diseases caused by fine particles on Earth. Over long periods, this exposure could significantly increase the risk of cancer and cause damage to DNA. If the outside environment is this hostile, where could humans possibly live? To survive for extended periods, humans will need specialized shelters. Bases designed to protect against the intense cold, radiation, and extremely low pressure of Mars. For decades, scientists and aerospace engineers have focused on a fundamental solution: fully sealed living bases, commonly known as habitats. A habitat on Mars is essentially a miniature artificial ecosystem. Inside it, every element essential for life, air, pressure, temperature, and water, must be carefully controlled. The internal pressure of a habitat may be maintained slightly lower than that of Earth. Temperatures inside are typically kept between 18 and 24 degrees Celsius, creating an environment similar to the conditions humans are accustomed to on Earth. But building a pressurized structure on a distant planet is far from simple. Because of this, scientists are increasingly focusing on a key strategy in space exploration: using local resources, a concept known as in situ resource utilization. One of the most widely studied ideas is the use of 3D printing to construct structures from Martian soil. The surface of Mars is covered with a layer of rock and dust known as regolith, a mixture of fine dust, sand, and crushed stone. Experiments on Earth have shown that regolith can be mixed with polymers or melted using heat to produce construction materials as strong as concrete. Mars is also home to enormous geological structures known as ancient lava tubes, tunnels formed when flowing lava cooled and hardened on the surface, while leaving hollow channels beneath. If humans were to build bases inside these tunnels, the thick rock above could act as a natural shield, protecting them from cosmic radiation, micrometeorites, and extreme temperature fluctuations. Some proposed designs involve inflatable modules transported from Earth and then expanded on the surface of Mars. Once covered with thick layers of soil, these structures could become spacious living areas while requiring relatively low transport mass. The earliest bases might house only 4 to 10 astronauts. But over time, they could expand into larger settlements. Inside these bases, humans would live in an environment designed to resemble Earth as closely as possible. And among all the resources necessary for survival, one stands above the rest. Not oxygen, not food, but water. Where exactly is water on Mars? And could humans one day extract it to survive on the red planet? The first clues appeared when orbiting spacecraft began capturing high-resolution images of the Martian surface. Across the planet, scientists noticed geological features that look strikingly similar to those formed by water on Earth. Eroded valleys, ancient river channels, and vast deltas. One of the largest of these systems is Valles Marineris, a colossal canyon stretching more than 4,000 kilometers in length and reaching depths of up to 7 kilometers. Certain regions within this massive rift display clear signs that ancient water once flowed there billions of years ago. Ground-penetrating radar from orbiters such as the Mars Reconnaissance Orbiter provided crucial answers. Its SHARAD radar instrument can penetrate beneath the surface and detect layers of ice hidden underground. The results revealed that many regions of Mars contain subsurface water ice located only a few meters below the surface. These frozen deposits consist mainly of water ice mixed with layers of carbon dioxide ice. Based on orbital data, scientists estimate that the total amount of water ice stored in the Martian polar regions would be enough to cover the entire planet in a global ocean roughly 20 to 30 meters deep if it were to melt completely. That is an enormous reservoir of water, yet extracting water on Mars is far from simple. The ice is often mixed with solid rock and soil, forming a material known as permafrost, permanently frozen ground. To retrieve water, robotic systems or excavation machines would need to drill, crush, and heat the frozen soil in order to release water vapor from the ice. Inside a Martian base, water would be continuously recycled. Systems similar to those used on the International Space Station today can recover more than 90% of used water, including moisture from breath, sweat, and wastewater. Water would also play a crucial role in space agriculture. Crops grown in controlled greenhouses require water to grow, while also producing oxygen and absorbing carbon dioxide. This means that water on Mars would not only help humans survive, it could also provide fuel for spacecraft returning to Earth. Yet the presence of water does not mean humans can breathe, because the Martian atmosphere contains almost no oxygen, the element essential for every complex organism on Earth. If humanity cannot carry oxygen from Earth forever, could we one day produce oxygen directly on the red planet itself? For many years, that question existed only as a theory. But in 2021, a small experiment on Mars demonstrated for the first time that it could truly become reality. The experiment is called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. During its first test in April 2021, MOXIE produced about 5 grams of oxygen in 1 hour. That is enough for an astronaut to breathe for approximately 10 minutes. That number may sound small, but the critical point is that the principle has now been proven. It is possible to transform the Martian atmosphere into oxygen. If this technology were scaled up, future oxygen production systems could be hundreds of times larger than MOXIE. According to NASA studies, a full-scale oxygen plant on Mars would need to generate around 2 to 3 kilograms of oxygen per hour to support a small crew of astronauts. Instead of transporting all fuel from Earth, something that is nearly impossible, spacecraft could produce their fuel directly on Mars before humans even arrive. Autonomous robots would land first, assemble oxygen production facilities, and begin storing tens of tons of liquid oxygen. By the time astronauts set foot on the red planet, the fuel for their return journey would already be waiting. It is a revolutionary idea in space exploration. It transforms Mars from a distant destination into a resource-producing outpost. Yet oxygen is only one part of the survival equation. Humans do not only need to breathe, we also need food. Every day, every month, every year. On a cold, barren planet where the soil contains toxic chemicals, growing food may become one of the greatest challenges of all. Could plants actually grow beneath the red sky of Mars? On the surface of Mars, there is a danger that cannot be seen with the naked eye. It is cosmic radiation, one of the greatest challenges facing any human who hopes to live on the red planet. The Martian atmosphere is extremely thin, with a surface pressure of only about 6 millibars, less than 1% of Earth's atmospheric pressure. During the journey to Mars, the Radiation Assessment Detector, RAD, mounted on NASA's Curiosity rover, measured an average radiation level of about 1.8 millisieverts per day. Compared to conditions on Earth, this number is astonishing. In just about 2 days, an astronaut traveling to Mars could receive roughly the same amount of radiation that an average person on Earth receives over the course of an entire year. Cosmic radiation is not simply a number on an instrument. It consists of extremely high-energy particles, primarily protons and heavy atomic nuclei, moving through space at tremendous speeds. Some of this damage can be repaired by the body, but other damage may lead to genetic mutations, increasing the risk of cancer, neurological disorders, or cardiovascular disease later in life. In addition to the constant background of cosmic radiation, another danger exists that is far less predictable: solar storms. When the sun releases enormous bursts of energy, known as solar particle events, billions of high-energy particles can surge through interplanetary space. Because of this, engineers are searching for ways to create artificial shielding to protect human explorers. One of the simplest and most effective solutions is the use of hydrogen-rich materials, such as water or polyethylene, to absorb radiation. On the Martian surface, bases may also be built underground or covered by thick layers of soil and rock. Yet, even if we find ways to reduce radiation exposure, the human body must still face another serious challenge. When humans leave Earth for extended periods, not only does the surrounding environment change, the human body itself begins to change as well. In the prolonged low-gravity environment of space, bones gradually lose density, muscles shrink, and the cardiovascular system must adapt to entirely new conditions. And this becomes the next biological challenge awaiting astronauts on the journey to Mars. A place where the human body may begin to weaken in ways that scientists are still striving to fully understand. In a microgravity environment, the human body almost completely loses the sensation of its own weight. At first, this can create a strange sense of freedom. Astronauts can float effortlessly through the cabin, moving from one place to another with only a gentle push. One of the systems affected the fastest is the muscular system. Because on Earth, every step forces large muscle groups to work constantly against gravity. In microgravity, those muscles are no longer required in the same way. And after only a few weeks, the body gradually begins to shut down muscles that are rarely used. In the absence of gravity, this balance is disrupted. Bones slowly lose minerals, particularly calcium. Bones and muscles are not the only systems affected. The cardiovascular system must also adapt to an entirely different environment. Nearly 70% of astronauts who have spent extended periods aboard the International Space Station have experienced a condition known as SANS, Spaceflight-Associated Neuroocular Syndrome. This condition can cause blurred vision or even long-term changes to eyesight. For a mission to Mars, the challenge becomes even more complex. Once they arrive on Mars, they must begin operating in an environment where gravity is only about 38% of that on Earth. To counter these effects, astronauts aboard the International Space Station rely on specialized equipment such as tethered treadmills, stationary bicycles, and resistance-based exercise systems designed to simulate weight. These workouts help slow the loss of muscle and bone mass, but they cannot stop it completely. Because of this, one major question continues to be studied. Can the human body truly adapt to living long-term in a low-gravity environment like Mars? The journey to Mars is not only a technological challenge, it is also the largest biological experiment in human history. Yet, even if humans can overcome these physiological changes, another challenge remains, one that is far less visible. It is the profound isolation between two worlds. Once astronauts set foot on Mars, they will be hundreds of millions of kilometers away from Earth, and almost completely separated from the entirety of human civilization. In such an environment, a small group of astronauts may have to live together for years inside a sealed habitat. Separated from loved ones, families, and the broader fabric of human society. For months at a time, they remain completely isolated from the outside world, communicating only with delays similar to those that would occur on Mars. The results suggest that humans can adapt, but not always easily. Researchers observed rising psychological stress, feelings of loneliness, mood fluctuations, and sometimes conflict among crew members. Psychologists will play a critical role in identifying individuals who can cooperate effectively, regulate their emotions, and maintain mental stability in an environment of prolonged isolation. Some researchers even suggest that future Martian bases must be designed with psychological health in mind. Artificial lighting systems could replicate the natural day-night cycles of Earth. Living spaces may need to be large enough to reduce the sense of confinement. Astronauts would also need to maintain regular contact with their families through video messages and communications, even if they must accept the unavoidable delays in signal transmission. Can human beings truly maintain psychological stability while living hundreds of millions of kilometers away from Earth? Could a small group of people build a miniature society on an alien world? These questions are already being explored today. The race to Mars quietly began many years ago. But in the past decade, it has begun accelerating at a pace never before seen in the history of space exploration. The United States Space Agency, NASA, is developing a long-term roadmap aimed at sending humans to Mars sometime between the 2030s and the early 2040s. The Artemis program is focused on establishing a sustained human presence on the Moon first. In this vision, the Moon becomes a kind of testing ground for technologies required to survive beyond Earth. Life, support systems, water recycling, oxygen production, and self-sustaining habitats. At the same time, the private sector has entered the race with remarkable intensity. SpaceX is developing an interplanetary transportation system known as Starship. It is one of the largest rockets ever designed. Once fully operational, Starship could carry more than 100 tons of cargo into low Earth orbit. The effort is not limited to the United States and private companies. China has also announced ambitious plans for the coming decade. Following the success of the Tianwen-1 mission and the Zhurong rover in 2021, the China National Space Administration is studying future missions, including efforts to return samples of Martian soil and rock back to Earth. Europe, Japan, and many other countries are also contributing to Mars-related research and technology development. Rare yet enormous events, asteroid impacts, extreme climate shifts, or cosmic-scale disasters have the potential to radically alter the habitability of an entire planet. Will Mars truly become humanity's second home? Or will it remain only a fragile outpost suspended in the vast emptiness of space? Mars is not a paradise waiting to be discovered, but a harsh test of the limits of technology and the instinct for survival. On this world, every fundamental element required for life, from oxygen to breathe, to water to drink, to food to sustain the body, does not exist in a readily usable form. For this reason, settling Mars is not simply an act of exploration, but a profound transformation that could mark the moment humanity becomes a multi-planetary species. And when the first human footprints press into the iron oxide soil of Mars, that moment will mark the instant life itself breaks beyond the boundary of a single planet and begins humanity's endless expansion into deep space.
Falling behind schedule. Habitat 2 needs stabilization now.
Roger that. Sending the team over. Keep me updated on the pressure.
we approach from the northern canyon, we minimize dust interference.
Agreed. That landing site looks promising, right near the
The radar altimetry confirms this site. If we route the rover here, we minimize risk.
Absolutely. The data looks solid.
Let's finalize the entry profile. We have less than 5 minutes of oxygen left.
I see the module.
Prepare for depressurization.
Mission Control, this is Eris 3. We have stable comms and positive power flow from the arrays.
Confirmed. Proceeding with oxygen activation sequence.
Oxygen system reports nominal levels. Activating communications.
Houston, do you read?
Connection secure. Moving to the next panel.
Copy that. Wiping dust from this section now.
I'm telling you, that simulation nearly took us out.
You exaggerate everything. It wasn't that bad.
She's right, Commander. We had it under control.
Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.